Hi, I'm JJ, and in this video I'll be doing a short demonstration that will show you how you can use your 850 interface and Pascal Capstone software to create a frequency response profile for a speaker. To do this, I'll be using two sensors. The first is a black Science Workshop sound sensor. We'll be using that sensor to measure the output frequency from the speaker. And the second is a blue Passport temperature sound level light sensor. This sensor is going to be used to measure the output sound level from the speaker. The speaker we're going to be using is a homemade speaker that I made using a paper cup. It was real simple to make. I used a few household items and some hot glue, and let me show you how I did that. First thing I did was take a magnet and glue it to the bottom of the paper cup. Then I took a small air core solenoid or a coil of wire and glued it to a popsicle stick. Then I glued two standoffs, in this case they're push pins, on opposite ends of the bottom of the cup. And then I glued the popsicle stick to the standoffs such that the air core solenoid was just over the magnet. Not a great speaker, but for this application it'll work just fine. I'll be driving the speaker using the output function generator on the 850 interface, and to control that output I'll be using Pascal Capstone software. So let's go ahead and take a look at the software and see what we're working with. As you can see here, I already have two displays set up in the software. The top is a fast Fourier transform display showing the data from my Science Workshop sound sensor. And the bottom is a sound level versus output frequency graph, which is going to show the data from my Passport temperature sound level light sensor. As I mentioned, we'll be driving the speaker using the output function generator on the 850. So let me go ahead and explain the controls that I have set up already. As you can see, we'll be driving the speaker using a 1-volt sine wave, and we'll be sweeping through a band of frequencies starting at 100 Hertz and ending at 5 kilohertz. The sweep should take 20 seconds, and the step frequency should be 0.1 Hertz. In addition to those controls, I also have set up a stop condition that's going to allow the software to automatically stop recording data when the frequency reaches 5,000 Hertz, or as you can see here, the output frequency is above 4,999 Hertz. So now that I have the software all set up and the hardware is ready to go, I'm going to go ahead and collect some data. And there you go. As you can see from the data, our homemade speaker does not do a great job at responding at higher frequencies. The best response from the speaker was between about 700 Hertz and 1.5 kilohertz, which is what we'd expect considering it's made out of a paper cup. To compare, what I can do is use a professionally manufactured speaker like the one I have here, and we can collect a response curve for that one as well. And to do that, I'm just going to go ahead and unhook the homemade speaker and plug in this professionally manufactured one. After I adjust my sensor just a little bit, we should be ready to go. And I'll go ahead and collect some data for that speaker. And there you have it. As you can see from the data, the professionally manufactured speaker does a much better job at responding at higher frequencies. And in general, the graph itself is much flatter, which means the speaker responds equally as well at that band of frequencies. And it's what we should expect considering this speaker is designed to make sound and this speaker is designed to drink coffee. So thanks for joining me for this demonstration. If you'd like to get a copy of this Pascal Capstone configuration file or a 60-day trial version of the software, you can do so at this website. Thanks.